Welcome back. Today we're talking about muzzle velocity and how they relate to the shell star. So before we begin, we need to talk about similar triangles. In previous videos in the series, I've alluded to similar triangles, and really, it's a standard thing in geometry you should have learned about back in high school, assuming you're out of high school. And there's plenty of YouTube videos that cover similar triangles. Feel free to look those up. The basic property of similar triangles that the shell star exploits is the fact that as long as all the internal angles of a shell star are consistent, that you can scale them up and down without loss of resolution, basically. So for example, we have our base triangle right here. We have our three sides, x, y, and z. If we take this triangle and shrink it to half size, all the sides will also shrink proportionally. So we have half x, half y, half z. Similarly, if we take the same triangle and double it in size, each of the sides will also be twice the length. So this triangle right here is twice the size of this triangle, so each side is also twice as long as the side it was derived from. And this is used in shell star calculations extensively because our crossing vector and muzzle velocity are both measured over the course of a turn, or 8 segments. But because triangles, for example, this was 8 segments instead of 2, we can shrink this down easily and keep the same results. So let's talk shot geometry table. The shot geometry table is what we use to figure out what our aim adjustment is over here. That tells us if we're going to aim directly at our target, 30 degrees or one window away from the target, or two windows or 60 degrees away from the target. That's so we can lead the shot, so we'll have a proper intercept calculation. As you can see in our triangle right down here, we have our crossing vector and our muzzle velocity. E is the course angle offset, which we talked about in the previous video. And the aim shift angle is really the thing we need to calculate today. So if we break this down even further, this is our same rate of closure, crossing vector, muzzle velocity triangle, except we broke it out into the two separate sub-triangles. So point B and point B are actually the same point. We just separated them out so it's a bit more clear what's going on. The information that we know is we know the crossing vector. We know the muzzle velocity, because when we launch a shell star, its muzzle velocity is 16 hexes per turn, 24 hexes per turn, and so on. We saw in the previous video how the course offset angle was calculated. So we have 3 knowns and 1 unknown. So how can we calculate this unknown? Well, basically it's this point up here, D. Again, because we're using similar triangles, we just expand things out or normalize them. So we're at 1 turn of flight time for crossing vector and 1 turn of flight time for projectile. And so in order for the intercept to work, they both have to meet at point D up here. So going from here to here, so think of this is the muzzle velocity, it's a constant. So to figure out the angle, we just have to drop this down until it hits the black line down here, which is the angle from the attacker to the target at launch time. So if you just think of this as a pivot point right here, we swing the muzzle velocity down until we hit the line. If we have a much larger muzzle velocity, for example, we added this little green segment onto it, so it's twice as long. When we drop it down to the line, this angle right here is much more shallow than this angle here because it has a smaller velocity and thus needs to lead the target more. So faster velocity, the more shallow the angle because you don't need to lead the target as much. So how do we calculate what that angle should be mathematically? Well, if we look at, again, the triangles and use a little bit of trigonometry, we have this segment right here, the height of the triangle, of the BD segment, or DB segment. By dropping this segment right here, we create two 90-degree triangles, ABD and BCD. And then we can use our trigonometry. So we know from trig that the height of BD is the crossing vector magnitude, which is this line right here, times the sine of the course offset angle. That will give us BD. From the muzzle velocity side, we know that BD is the muzzle velocity times the sine of the aim shift. And since both equations come out to the same result, we set them equal to each other. So the crossing vector times the sine of the course offset angle has to be equal to the muzzle velocity times the sine of the aim shift. Again, standard trigonometry you probably learned in high school. If not, again, plenty of YouTube videos out there that talks about trigonometry, triangles, more importantly, the sine function. And so solving for aim shift, we have crossing vector divided by muzzle velocity times the sine of the course offset angle equals the sine of the aim shift angle. At this point, we could also then take the arc sine of both sides and do a little bit more mathematical manipulation, but we don't have to worry about that. The Play 8 actually does the math for us. We just need to know that this is the course offset angle, this is the crossing vector, muzzle velocity, and aim shift. This little extra mathematical function really does not come into play in the, well, it comes into play in the Play aids, but we don't need to know how it actually works out in terms of math. So if we go to the shot geometry table, we brought our equation over here, and we can see how it maps up. The course offset angle part, this part in green right here, we know from previous videos, determines which column that we use. So if our course offset is 4, we'll use this column right here. The whole sine part's already been calculated into the values, so you don't need to worry about that. Same thing for the sine part over here. And finally, to figure out which ratio we use, it's this ratio of crossing vector to muzzle velocity. So if it's a 1-to-1 ratio, we use this box right here, which is aim shift 1 or 30 degrees. Cross-referencing, we know, hey, it's a 90% adjustment to the muzzle velocity. We'll be using this row right here. So again, crossing vector, muzzle velocity maps to these ratios as so. The ratios are also, we do a lot of rounding, as we'll talk about in the next couple slides. Next couple slides. Rounding, rounding, rounding. The way the game is set up, all the angles are multiples of 30 degrees. So we have a course offset of 6. That's actually anywhere from -15 to +15 degrees, with 0 being in the middle. And we really don't use the negative part of that. We have a course offset of 4. That's anywhere from like 45 degrees to 75 degrees, but we typically use the median value of 60 in our calculations. Aim shift is the same way. An aim shift of 0 is anywhere from 0 to 15 degrees. An aim shift of 1 is anywhere from 15 degrees to 45 degrees. Aim shift of 2 is anywhere from 45 degrees to 75 degrees. And an aim shift of 3 basically doesn't happen because you're firing at, perpendicular to your target's path of travel, so you're really not going to hit anything. That's an aim shift of 3, which is no shot. Now let's take a look at what this looks like graphically. So here we have our muzzle velocity in red, and the length of the line is the magnitude of the muzzle velocity, so or how fast the shot is going out. Over here, we have our crossing vector. That's the direction of the crossing vector. And again, the length of the line is showing you how fast the ship is moving relative to the attacker, or it's the magnitude of the crossing vector. So to figure out which aim shift region we're going to be in, we just simply slide this arrow over until it touches the red circle, like so. So by shifting the arrow over until it touches the red circle, here we have our two triangles. So triangle 1 with the muzzle velocity, you can imagine the little dotted line coming down, and then our crossing vector and our course offset angle in here. And so we know that this line right here, where the muzzle velocity is within the aim shift to 0 region, so this would be a straight on shot. Now, if we double the size of our crossing vector, but keep the same angle, you can see that we've shifted up to this aim shift 1 region, because again, this would be the actual line that intercepts, as then we drop down to the rate of closure line to get our two triangles. But because it's in the aim shift 1 region, we count this as a 30-degree leading shot. And we double the length of the crossing vector yet again. And as you can see, it actually crosses inside the circle, which is fine. We only care where the arrowhead hits, and it's up here in the aim shift 2 region. And here's all three arrows at the same time, so you can see how it looks. Now, if the ship is flying away from us, the crossing vector will be pointing in roughly the same direction as the shot. So this has a few different implications. So for this first one, again, it's an aim shift 0 because we just keep dragging it over. We just keep dragging it over until the arrowhead touches the circle, which would be right here. So this is our actual shot, and so it's an aim shift to 0. As see, our crossing, our rate of closure line will actually be this part down here, because we're getting away. Our ship is flying away from the attacker, or the target's flying away from the attacker, depending on your point of view. If we double the magnitude of the crossing vector, you can see we're now up into the aim shift 1 region. And again, our rate of closure keeps shrinking because our ship is flying away, so we're taking away from the overall speed of the attack. And here we double the crossing vector yet again. In this case, there is no intercept possible because the target is outrunning the projectile. There's no way the gun can be targeted, so it'll actually intercept the ship. It just flies too fast and will basically escape. So again, these are all three of the ship flying away. This is a constant angle of about 30 degrees. And probably closer to 45. Flying away from the attacker and how the intercepts are calculated. Well, that is basically everything you need to know about how the aim shift modifier is calculated. We've gone over where the shot geometry table comes from, how those ratios are calculated, and what it actually looks like geometrically. This next series of slides, which you definitely do not need to know at this point at all, will basically walk through all the different combinations listed on the shot geometry table so you can see what they look like. Unfortunately, all the values are rounded to the nearest 0.5 for playability. So the ratio between the crossing vector and muzzle velocity is rounded to the nearest 0.5, so 0.5, 1, 1.5, and 2, mostly for playability. And definitely not accuracy. There's a couple places where you're like, oh, that's not accurate at all. But it was rounded to be playable. And as you start looking at this, you start to go cross-eyed really fast. So I'm just warning you, you definitely do not need to know anything beyond this slide. And in fact, it's best you don't look at anything beyond this slide and just review the previous section of this video if you have any questions. But if not, we'll go for it because, hey, if we're not anything, we're thorough. But before going on, if you like this video, please give me a thumbs up. If you want to see more videos like this in the future, please subscribe so you get notifications. And comments are always welcome down below. If you have any questions about how any of this stuff works, feel free to ask and we'll answer. We might spawn more videos. Okay, with that said, let's go on. So, shot geometry table. Course offset is 6. So right down here we have our crossing vector. It's heading directly towards the attacker, and the attacker is shooting directly back. That's probably the simplest case. So yeah, we're always going to be shooting directly at it, and so on. Okay, course offset of 5. So this is a 30-degree angle. And this is the 1-to-1 ratio. So each of these lines here is the same length as the muzzle velocity lines. And again, the key thing to focus on for these slides is this less than symbol. So we're trying to find the upper boundary of these aim shifts windows. So for here, we round this down to the 15-degree angle because that will intercept nicely with this angle right here. So anything less than 1-to-1, we round down to aim shift 0. If we change our crossing vector out to 1.5, you can see that it'll intercept the 45-degree angle right here. So we round everything down to 30 degrees or aim shift 1. And if we get a 2-to-1 ratio, as you can see, this is twice the length as the muzzle velocity, and we will not intercept at all. None of these will actually intercept. This line up here will actually be slightly above the circle. So there's no way for a ratio of greater than 2-to-1 will ever be hit by this muzzle velocity because the shot's just going too slow. But for purposes of less than 2.1, we'll round down and it roughly corresponds to the aim shift 2 region. So if this was slightly slower, our angle drops slightly and will intercept this point and will be the aim shift 2 region. Okay, course offset of 4. This is a 60-degree angle. Again, we use the 45-degree line here. It's fairly close to this line right here. So we'll round everything that's 0.5 to 1, or half the size, to aim shift 1. When we get to the 1-to-1 ratio, you can see this line right here, which is 45 degrees, will map to this angle here, which is also 45 degrees. So anything that's less than 1-to-1 will map to aim shift 1. The key thing again is the less than symbol. 1.5, again, we're using the lower bounds of that angle to basically say, hey, it'll intercept roughly right about here at aim shift 2. And so anything less than 1.5 will call as aim shift 2. And then anything above it will not be able to be hit at all. As you can see, 1.5, the true angle is the center line right here, and it's way above the size of the circle, so there's absolutely no way for this thing to actually hit. Okay, 3. This is one where it is actually highly inaccurate because, again, we round to 0.5 instead of 0.25. As you can see here, course offset of 3 is 90 degrees straight up, and aim shift 2 really should be half that, or 0.25, but because of game design decisions, to go to 0.5, anything that's 0.5 or less gets rounded down to aim shift 2, even though we have this region up here where it's clearly aim shift 1. And then, continuing the trend, here is aim shift, this is the 1-to-1 ratio. As you can see, 0.5 would it be about, right here, so it would be clearly an aim shift 1 will still be fine if we said 0.5 instead of 1-to-1. And a 1-to-1 is, well, actually, greater than 1-to-1, we won't be able to hit it all because it's going too fast. As you can see, 1-to-1 is literally the top of this arc right here, so anything greater than that will be outside the circle. But we round this down to aim shift 1. Personally, I would have gone 0.25, 0.5, and less than 1-to-1 and gotten all 3 in here, but I'm not the game designer, and the game designer decided that stick to 0.5 levels. I did warn you that this was insanity-inducing. Okay, now we are course offset is now pointing away from the attacker. So this will move to inside the circle. So here, 0.5. So the crossing vector is less than half the size of the muzzle velocity. So this all gets rounded down to aim shift 0. Because it's this line apart right here is fairly close to here, so we round down. 1-to-1 is literally overlays the aim shift 2 line. So if we were looking at less than 1-to-1, it all gets rounded down to aim shift 1. And obviously, as we're already at the circle at 1-to-1, anything beyond that will be above the circle and we won't be able to hit. Course offset of 1, that's heading 150 degrees away from the target. And that matches up perfectly with the aim shift 1 area, but as we're looking at the less than sign, we count it all as aim shift 0. And anything beyond 1-to-1, obviously the arrowhead would be out here, and thus the muzzle velocity will never be able to catch up with the fleeing ship. And finally, course offset is 0, which is target is heading directly away from the attacker. It is always the bearing window or aim shift 0, as long as it's less than a 1-to-1 ratio. If it's greater than a 1-to-1 ratio, obviously, once again, the ship would be flying too fast for the shot to catch up. Okay, and that is the end of the muzzle velocity. As you can see, if you stuck through the final slides there is a lot of rounding in the table, and some of it is not all that accurate, especially for a course offset of 3. Everything else, if you squint really hard, you can kind of justify it. But again, it's a design decision between playability and accuracy, and with a lot of play testing, numbers mostly work out. So anyways, as I pitched earlier, if you like this, please give me a thumbs up, especially if you sat through the last couple slides going over the different angles. If you'd like to see more stuff like this, please hit the subscribe button, and comments are always welcome down below. Have a nice day. I'll catch you later.